Complexity in physics isn't about harder math, it's about connecting simple parts in clever ways. This soft body jelly is just a network of individual springs working together to maintain its shape. In the world of Spider Man, the web is more than just a rope. It's a dynamic tether, whether you're swinging through the neon streets of New York as Miles Morales or navigating the stylized worlds of shattered dimensions. The web reacts to weight. It stretches, it stores energy, and it snaps back. In game physics, we don't treat a web as a static stick, we treat it as a spring. And the math governing that spring is what gives objects their jiggle, their weight, and their life. Hi everyone, I'm Amlan Pati. In our last video, we looked at how distance creates gravity. Today, we're using that distance to create connectivity. We are coding Hooke's law to build everything from bungee cords to soft body jelly. Let's get to work. Everything in physics wants to be at peace. We call this equilibrium. A spring is only happy when it's at its rest length. If you pull it away from that length, it pulls back. This is Hooke's law. Force equals stiffness times displacement. If you pull a spring twice as far, it pulls back twice as hard. By applying this logic to our code, we can create constraints, rules that keep our particles tethered to a specific point or to each other. Back in VS Code, we are using our standard Emmet shortcuts to prep the canvas. Now don't worry if this part feels repetitive. Every physics simulation starts with the same foundation: a canvas, a rendering context, and a loop that updates every frame. Think of this as building the stage before the actors start moving. Right now, we are not doing physics yet. We are just preparing the world where physics will happen. We need a mouse anchor and a single particle. This will be our Spider-Man at the end of a web line. And this mouse position is going to become our anchor point, like the wall where the spring is attached or the building Spider-Man is swinging from. So even though it's just coordinates, conceptually this is the fixed end of our tether. Whenever we simulate motion, we always need position and velocity. Position tells us where the particle is. Velocity tells us where it's trying to go. And by updating velocity over time, we get acceleration, which is where forces enter the system. I am also giving the particle a radius, not because physics needs it, but because visuals matter. Seeing the object clearly helps us understand how the motion behaves. We are defining our physics constants. K is our stiffness. At 0.05, we'll get a nice stretchy feel. And our rest length is 100 pixels. That is the sweet spot where our spring will stop pulling. These two constants are basically the personality of the spring. Stiffness decides how aggressive the spring is. Rest length decides what distance feels normal. We'll be adding a third constant later. Alright, this is the heart of the entire video. Everything we associate with jiggle, bounce, elasticity, or soft body motion comes from what we are about to write next. So take your time here. This is the core formula behind animated life. Let's evolve our gravity code into spring code. First, we calculate the distance to our anchor. This is the exact same math we use for gravity. Distance tells us how far reality has drifted away from equilibrium. But here is the change. Instead of just using distance, we find the stretch. This is the difference between where the particle is and where the spring wants it to be. And notice, we are not applying force yet. We are just observing the current state of the system. That's what simulation is. Measure first, react second. This line right here is incredibly important. Now we calculate the force. We multiply our stretch by the stiffness. If the stretch is positive, the force pulls back. If it's negative, the spring actually pushes away. This is how we simulate tension. The negative sign is what makes it restorative. That minus sign is physics saying, return home. Now we convert that force into motion. In full physics, we divide by mass, but for games we often assume mass equals 1. That keeps the math clean and the motion believable. And we divide by distance here because we want direction. This is how we turn a raw force magnitude into a force vector. So the spring isn't pulling randomly. It's pulling precisely towards the anchor. The particle starts to oscillate. It bounces back and forth around the equilibrium point. To make it look like a real web and not a chaotic vibration, we add damping. We also have our damping at 0.92 to prevent infinite bouncing. We bleed off 8% of the energy every frame, allowing the jiggle to eventually settle. That is the secret to satisfying physics. Damping decides how quickly the energy fades out. With these numbers, we can control whether something feels like a rubber band, a bungee cord, or a rigid steel rod. This is one of the most important tricks in game physics. Without damping, energy never dies. The particle would bounce forever like a perfect mathematical pendulum. But real worlds aren't perfect. Friction exists. Air resistance exists. So damping makes our simulation feel physical, rounded, and satisfying. A jelly blob is not one object, it's a conversation between particles. Every spring is like a tiny agreement. Stay close, but not too close. And when all these agreements happen together, you get squish, you get wobble, you get life. And once you understand springs, you have unlocked one of the most powerful tools in simulation. Springs create ropes, cloth, muscles, and jelly. So experiment. Break the system, stretch it too far, make it unstable. That's how real physics programmers learn. So, how do we go from a single string to a complex jelly blob? Think of a bicycle wheel. A soft body is just a collection of particles where every dot is connected to a center point and its neighbors using the exact same spring math we just wrote. In the advanced version, I have added a circle of 12 points and a gravity constant of zero point 0.5. When you drag the skin, the internal springs pull the rest of the body along, and the floor collisions create that satisfying squish. Solve the challenges in my GitHub and comment if you found them helpful. Next time, we are going to learn how physics sees the world through raycasting. Like, share, and subscribe, and I'll see you in the next one.